Okay, now we finally get to combine everything you've learned into looking at the whole planet, the whole planetary circulation of the atmosphere. We're looking at the big picture. We're not coming down to where you are, anything like that with this time. We're going to look at the globe as a whole this week. So with that, we're going to just look at some of the principal features, basically the climate. To think about it, if we had an idealized world, we had nothing but sunlight or darkness, no rotation. So we always have the hottest temperatures in the most direct sunlight, right? And the coldest temperatures where it never could see any sunshine at all. So you would have a massive circulation that just basically went uplifted, around, and back down. So you would do it in the southern and northern hemisphere. But guess what? We got a rotating Earth. So the rotating Earth means everything in the northern hemisphere turns to the right. Everything in the southern hemisphere turns to the left. And so with that, we wind up splitting because of the speed we have of the rotation, so that we have basically low pressure, high pressure, and all. And you can see this in a global map here. And I want to show you quickly, just look back over here a minute. And here is a kind of a pseudo surface map, but it matches up. Think about it. 30 degrees north, lots of high pressure, high pressure. So these are the kind of the subtropical highs. Low pressure is up closer to 50 to 60 degrees north, lows, 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 all wrapping around here. And then you have the polar region. So kind of interesting to see how that all works out. So but we can go on with this, and you get this. We talked about the subtropical anticyclones. Well, think about it. There's one along 30 degrees north over the Atlantic Ocean. So if you're located in the southeastern U.S., you're on the western side of that, right? So what's the western side do? That brings up moisture from the south. It has less stability, frequent episodes of cloudy and stormy weather. However, if you're on the other side, which in this case would be over in the deserts of Sahara, guess what? They have compressional warming, low relative humidity, fair skies, and most major deserts are located on the eastern flanks. Guess what? We have an eastern flank over the Pacific that extends into parts of Southern California, where we have more of a desert climate. We have the poleward side, we have the polar lows, and at the very top, typically we have an anticyclone that develops at the very highest latitudes. And then there's the polar vortex. This is a loft. It's a very strong feature that occurs in the northern hemisphere and the southern hemisphere. It reaches its maximum typically in the northern hemisphere, generally around February or so, and then begins to weaken after that. It's all based on the fact that there's no sun heating up there at that time. So it just gets colder and colder, and the winds spin faster and faster. Now, in the mid-latitudes, where we live, the winds generally go from west to east, and you can see they're like a trough, ridge, trough. And if you look at the contours of 500 millibar or 300 millibar, whatever level you want, you basically see this pattern. So with that, think about it. Tropopause, down by the equator, you have lots of heating. Remember, less dense air is going to push the tropopause higher, so it's pretty high. Mid-latitudes, you have lots of fronts going up and down through it. So you wind up having a tropopause come low, and tropopause going back up as the front passes back to the north. However, in the polar regions, basically it's in the Arctic air all the time, you get very low tropopause. So you can see we're in the area that tropopause varies a lot. And we have the trade wind inversions that occur down in the southern latitudes, basically you don't want to be going at 30 degrees north. If you were in a sailing ship, you'd want to be down around 10 or 20 degrees north. On the south side of it, you would get a steady wind from the east to the west, and that's how Columbus and them got over here. One of the other interesting things is the intertropical convergence zone. It kind of varies a lot over land, but not so much over the ocean. Well, the ocean takes a lot of heating to really get it to warm up. Remember, it absorbs a tremendous amount. Its latent heat is very high. So it absorbs a lot of heat before it's well warmed in the tropics. So it doesn't change a whole lot of temperature. So the intertropical convergence zone doesn't move much. Over land, on the other hand, much more. So you can see, for example, San Diego is on the western side, on the eastern side of the high, subtropical high. Look at very, very, very dry. Charleston's on the western side, much significantly more moisture. And here they are. Guess what? They also create ocean currents. We'll just look at ours, for example. We've all heard of the Gulf Stream here. We have this big subtropical high sitting here aloft, and it basically pulls the moist water coming up out of the Gulf of Mexico, up along the east coast, and then around the top of the high and up towards Norway. That is on the west side of the high. You have a Labrador current coming down. Oh yeah, on the California current, winds are coming out of the north predominantly. So what do you get? Cold water coming down from Alaska and all along the west coast of the U.S., making it colder. Because of these impacts over looking at the globe, you wind up with monsoons sometimes, where the wind can set in and just stays in a pattern, particularly relatively close to the tropics. And you can see here a wet monsoon coming into the Bay of Bengal in the summertime, where the intertropical convergence zone has moved north of the area, pulling lots of moisture in. In the wintertime, on the other hand, lots of dry air coming out of Siberia and all, making it almost never rain in that part of the world. We also have a monsoon, and then North American monsoon. What happens is it heats up over the mountains. Believe it or not, there's 5,000 to 6,000 foot mountains out here in Mexico. They heat up during the summer. By midsummer, they're getting quite hot. They've heated the atmosphere through a large layer out there. Low pressure forms. Remember, less dense air. When you get the low at the surface, you're getting high pressure aloft because, again, less dense. But what that does, it sits it in place, and you wind up with flow coming in off the Gulf into the low, bringing lots of moisture up into Arizona, New Mexico, southwestern parts of California, and even up into Utah and Colorado sometimes. So you can get this, and that's when they get their majority of rainfall out there. All right, Rossby waves, it's easier to show you on these. So we'll take a look at this. Rossby waves are long waves, we'll call them, in the atmosphere. This is looking down at the pole, looking at 300 millibars. You can see a jet, very fast jet moving here, another one here. Notice how they dip. There's a dip right here, a little bit of a ridge back up, another dip over here somewhere, maybe a big one. You look at this low right here, low here, 1, 2, probably a third one over here, maybe four big long waves in the atmosphere with a lot of little tiny short waves going through them. So a Rossby wave is a big wave in the atmosphere. You can see them more from the poles than you can from any other latitude. And you look down and you'll find where a Rossby wave is. That's where the flow will kind of dip down a little further south. So it's an area you look for. More lows developing, cold air may be coming down out of that area. And we can look at that. Actually, I let this go here, but if I were to turn it on, you can actually watch these waves kind of troughs rotate around them and down. You can see we have one developing in the eastern United States. Now, this is all models, so this isn't necessarily reality here in the future yet. One of the things that your stuff talks about is also damming. A pattern gets locked in, it doesn't change. Well, a lot of times in the wintertime, you get a Hudson Bay low. And you can see that this is up over Hudson Bay. So kind of has its main trough in the eastern part of the U.S. right now. You're building a ridge here towards Greenland with time. But the flow is just kind of flat across most of the U.S. It's not really deep troughiness right now. But you can see out here over Siberia, more of a trough. But it's just interesting to me, this watching this big ridge, and you see this little low down here south of that ridge. It's not moving anywhere. It's blocked. It's like an eddy in the atmosphere. So it's waiting for something to push it out. And here's what's going to push it out, it looks like. Kind of moves towards it and begins to eat away at it and gradually pushes it out. But now it's getting locked down there. So you have another one at this stage. So it's like a very good lows are keep forming down over there, that part off the U.S. East Coast, and they get locked in place there and not moving very fast. But this is just an example of looking at an overall global jet stream with the Rossby waves and short waves imposed. And you can see here, we talk about a lot of divergence on these short waves, on the jets. If you have a strong jet, left front quadrant tends to be where, so that's the beginning where you're coming into the jet, you're picking up speed, one area of divergence. Right rear quad is another area, which you might have here, it's turning around. So you can see actually it's not too bad. There's a little divergence right there. And sometimes you get where you have the left front and the right rear corresponding, and you get much greater divergence. And a lot of times that's where a big low will pop up. So if you looked at that, guess what? There's a pretty good sized low right there. So it actually works in theory. Now, some other things you're going to talk about this week are La Nina and El Nino. La Nina, cold, basically saying the tropics in the Pacific are going to be cold. We use Nino 3.4 region to look at an El Nino or La Nina. These are the anomalies from normal temperatures. Currently, we're almost up to 1.5 degrees. They consider anything greater than 0.5 degree over a 3-month time frame to correspond as a La Nina. So we had August, September, October. We're pretty much in La Nina. So what does La Nina mean? Well, let's go to that. Take a quick peek at it here a minute. And La Nina, they alternate a lot of times. You get the historical perspective here of how many La Ninas we've had and El Ninas. But they really shape a lot of what happens. They're kind of caused by the Ekman transport that you've learned about here. And an El Nino, or warm phase, you get lots more thunderstorms over the Pacific. It causes a stronger divergence aloft, more flow. The winds get a lot stronger over the Pacific and all. So you wind up getting a lot more rainfall on the west coast of the U.S. especially. And you may get a very strong jet moving across the United States, the southern part of the United States. It kind of keeps it all wet and cooler in the southern part of the U.S. La Nina, on the other hand, it's a little different and it's a little more complex. Really, your cold water extends all the way to the east coast, and it tends to cause a lot of droughts out west. in the Midwest, it doesn't allow the cold air necessarily to come down so well sometimes. So sometimes the cold air winds up staying right across the northern part of the United States. However, there have been instances where another feature that we talk about a little bit here, the North Atlantic Oscillation, takes over. And the North Atlantic Oscillation, remember I showed you lows and highs over the Atlantic rotating through there? Well, depending on which phase this is, whether it's a positive NAO or a negative NAO can really push down a lot of cold air into the eastern U.S. It also creates a lot of storms along the eastern half of the United States. And if it dominates during a La Nina winter, sometimes we can have extremely snowy winters. On the other hand, if it's a positive phased NAO, we're not getting that much cold air, and we're not getting nearly the amount of storms. We have a relatively dry winter, and we don't get the real big snowfalls. So this is kind of superimposed on the La Nina pattern. So it's another way of looking at things. The Arctic Oscillation is basically looking at the polar vortex. At the very top of the world, in the wintertime, there's a very strong rotation at the very top, big low, see counterclockwise. And if it weakens, you get some very strong Arctic outbreaks that come down. If it strengthens, you don't get a whole lot. Last winter, we didn't get a whole lot because it never weakened. It got stronger and stronger. Finally, they talk about the MJO. And Madden-Julian Oscillation. What it is areas of thunderstorms develop in the Pacific, the tropical Indian Ocean area, and they migrate to the east. They have been traced to cause major cyclogenesis around the globe. They basically make a transit around the whole globe in 30 to 60 days. And if you can track them, you can actually see them enhance cyclones with time. They're very difficult to track, but there are people that actually pay attention to this because it can give you a 30 to 60 day kind of forecast of what the weather might be in your area. Not day to day that much, but maybe over a week to 2 week long period. So, final thing I just wanted to show you was looking at the globe and looking at the intertropical convergence zone, because you can see it. Right here across the southern Atlantic is the intertropical convergence zone. Here it is over in the Pacific. And you can see where it is right now, north of the equator still, but moving southward slowly. So that's what this is all about this week, looking at the whole global picture of the weather. Next week, we're going to narrow it down into more details of our weather.